All right, so we're trying to find the electric field at this point P as affected by that. We know it's going to be going that direction-ish, kind of down that way. And you already said, and like we said, the x is going to cancel because in this x direction it's symmetrical, so it's going to be affected the same from both directions. So the integral we're going to use is this ke lambda dl over r squared times this r hat. And we're going to break this down into all of its pieces. So our r squared, we're just solving like r squared, that's like the hypotenuse of this. Our radius is this distance from P to anywhere on there. So that's going to be this big R squared plus D squared, because that's just a right triangle. If we connect it here, it's a right triangle that we rotate around, and that's going to give it, like, that's the distance to that thing at any point. So it's big R squared plus D squared. That's where that came from. And our equation here for with all of this, we need to find our DL, but our length is for like it's usually for like a straight wire. So in this case, our DL is going to be the arc length here, right? Because what we're really doing is the integral is sweeping around. So it's sweeping from here to here. What's changing is this position, but our L is our length of, it's like an arc length. So and our DL is, as it gets smaller, we're taking smaller and smaller pieces of that arc length. So if our L, then the equation for arc length is just theta in radians times our radius, which is this big R, because that's the radius of that big circle there. Then all I did was take the derivative of this with respect to theta. So I got DL, DL, and that's equal to R times d theta, because the derivative, if we're taking respect to constant, if this was just like 4x, taking the derivative, it's just going to be 4, but times whatever the change in x is. That's all this is. All right, we have our dl and we have our r squared. Now we're going to look at this r hat, right? So the r hat is just the direction, like we said, the direction of this r, which we said was the hypotenuse there. And that's being like rotated around, right? So at any given point, in our x direction, that vector is going to be going like, it's going this far in the x direction, so it's going r to start off with, and then a little bit less than r. So that's going to be the cosine, x direction is going to be the cosine of this angle in here, theta. Because remember, the theta is what we're like using to sweep around this edge. So in the x direction, the r hat's going to be r cosine theta. But since it needs to be a unit vector, since it's going to be a unit vector, we're going to divide by the length of this hypotenuse too, right? So that's going to give us the that's the x component of that vector, but we divide by the magnitude, and that's going to give us the unit vector. So that's just going to be big R cosine of theta, because remember, like we said at the beginning, for the beginning, when theta is 0, it's going to equal r. But it's going to be r, and then we're going to divide by that r there. And then we're going to look in the y direction. We're going to do the same exact thing. In this y direction, the vector is always going to be this length d. Or it's always going to be in this direction for d, but we're still going to divide by that r. So we're going to get plus d over r. That's our j hat. Right? And then, I'm writing this like backwards, but it's fine. And then we're going to look at our k direction. And we said that our x direction is cosine theta, so our z direction is just going to be sine theta, because it's going to be this opposite component over here. So that's our sine opposite, so it's going to be sine theta. It's going to be r sine theta, r sine theta over, and again, it's still over that big R. That's our k hat. And like we already said, we know this x direction is eventually just going to cancel out, so we can ignore that for right now, or we can just ignore that in general. And then if we look at the logic of the way our axes are set up, if we look at the direction it's going to be going, this way, down this way, that's going to be going in the positive y direction, but it's going down, so it's going to be in the negative z. So we can just change that here. Instead of it's plus y, it's going to be a minus the k hat. So once we plug, we have all the values that we need now, so we're going to plug them all back into here. Oop, I didn't close the parentheses. So our lambda stays the same, our ke stays the same. Then our dl, like we said up here, is going to equal our r d theta. Our r squared up here is going to be r squared plus d squared, and that's our r squared. And I, just for simplicity's sake, I changed it from a lowercase d to an uppercase d, just so we wouldn't get confused between d theta and this actual d, which is a value. And then I also solved this equation for r by square rooting both sides. Instead of writing it as a square root, I just raised it to the 1/2 power, which is the same thing. So when I plugged in my r hat, I had the d over r, which again is now this, d over r j hat, minus the r sine theta over our r k hat. All right, I got kicked out of the room, so it's going to be a little bit different lighting now, but it's still fine. So since we have this minus sign here, I just distributed in and split it into the two different integrals. So we have the lambda r d theta from that over the r squared plus d squared, and the multiplied by the d over r squared plus d squared to the 1/2 j hat minus the, again, this lambda thing, this whole mess here, this whole mess here, same thing. And now, since these have, like, they have an exponent, but they're the same base, I'm going to combine them, and it's going to be r squared plus d squared, all raised to the 3/2. All right, I just did some more combining over here as well, where I moved the d on the other side of the d theta, just for my own brain's sake. And then I combined, obviously, r times r is just going to be our r squared. But remember, this is big R squared, so we're not plugging anything back in for this. So now I'm just going to pull out all of the constants from each of the integrals. So it's, because everything, lambda is a constant, R was given by the graph as a constant. This uppercase D, remember, was just the same as this lowercase d. I just changed it for simplicity, for not getting confused with this lowercase d. So this is a constant, this is a constant, this is a constant. R and D are also both constants. This is a constant again. R squared is still a constant. This is still a constant. So almost everything can get pulled out of these, and I'll just do that real quick. I did also forget to mention, but this j hat and k hat, they're also constants. They're just constant vectors. So they can just be pulled out as well. And now we're just going to look at what are the bounds of our integrals, because I haven't done that up until this point. So we're integrating with our theta, and remember what we're doing to get this kind of like sweep around is this angle inside here is going to go from 0 when it's here all the way around, right? So it's our theta is what we're changing. So we're going to go from theta equals 0 to all the way around to theta equals pi. So we're going to be integrating this. Both of these is going to be integrated from 0 to pi, from 0 to pi. And it doesn't really matter how you do this. If you want to do like negative pi to 0, as it's going to be the same magnitude no matter what. So it's like, because technically if you look at a unit circle, this is like negative pi to 0, or if you want to go underneath, it's negative pi, whatever. Or if you're looking at it the other way, it could be like pi to 2 pi, or whatever. There's like 100 different ways to use it, as long as the difference between the two is 0 and pi. Because remember, that's just in radians, that's the angle that we're trying to go from here. We're going like here to here. Here's the circle. Ooh, that's a bad circle because the thing moved. We're going here around to here. 0 and pi, that's our angle that we're looking at. So now without all this mess inside, the actual integrals look pretty straightforward. So we have like d theta is just going to be theta, because obviously the derivative of just theta is going to be d theta, right? And then this one, obviously we have, since derivative of cosine would be negative sine, we're going to multiply both by -1. Derivative of negative cosine is going to give us sine. So our, well, technically it's sine d theta. You didn't even see that. All right. Technically it's sine d theta for both of those because that's our sine d theta. So we get negative cosine there. And now we're just going to plug in the bounds. I hate that I can't write and film at the same time, whatever. Now we're going to plug in the bounds into each of these. And I put them in parentheses because you don't really have to be plugging it in. There's nothing to plug it into over here. It's just going to, you're just going to have to distribute it in later. Or simplify this in the expression inside and just multiply it. So when we plug in the bounds to this side, it's just going to be pi minus 0, because again, it's the larger bound minus the lower bound, and that's just going to give us pi for that as the answer for that whole integral. And then this is negative cosine of pi minus negative cosine of 0. So our cosine of pi is negative 1, so it's negative 1 plus, because it's again negative minus minus, and our cosine of 0 is just 1, so 1 plus 1, 2, that one's pretty fine. And then we simplify it with everything else as well. All right, so we're going to start now we plug in all of these values, but I've been using KE this whole time for this constant coefficient. Remember, that's just our 1 over 4 pi E naught. That's the same thing. So when I plugged it in here, we still have our lambda RD, now multiplied as well by this pi, times our KE, 1 over 4 pi E naught, and with this whole mess still in the denominator, and that's our J hat. Then the same thing over here, we have our lambda R squared, times this 2 over here, the 4 pi E naught, and this whole mess in the denominator, that's our K component, right? Just wrote them up by accident. So we look over here, both top and bottom, the numerator and the denominator, are both being multiplied by pi, so that can cancel out. And we look over here, the same thing happens with the 2, except it's just going to cancel to have a 2 on the bottom, because that's just 2 over 4, 1/2, right? So when we look at our answers, we know that's 0 in the I direction, because we don't have an I direction, we're only looking in J and K. And then our J component is our 1 over 4 E naught. That's what we just canceled to, our over 4 E naught, times our lambda RD. Oop, focus please. Focus, there you go. Lambda RD over that whole mess. And remember, their lowercase d is the same as my uppercase d. I just changed it. So that's our lambda RD over that whole mess. That's our J hat component. And then when we look at for our K hat, we get the 1 over 2 pi E naught, which is what we just canceled to, the 1 over 2 pi E naught, and that's negative, because again, we're looking in the negative K direction, and that's times the lambda R squared and that whole mess. And that's our lambda R squared and that whole mass in the K hat direction.